Ever feel like you're just drowning in information?
Yeah.
Articles everywhere, research papers, you just can't even. It's like
Yeah.
trying to drink from a fire hose.
Totally.
Well, that's why we do these deep dives, right? We take all that information, we try to what's really important just for you.
That's right. We're like your personal research team,
Exactly.
digging through it all so you don't have to.
And today,
Mhm.
we are diving deep into one of the most fundamental concepts in AI,
Oh, yeah.
intelligent agents.
Absolutely.
We'll be pulling from the book Artificial Intelligence, A Modern Approach
Mm.
by Stuart Russell and Peter Norvig.
A classic.
And we're going to extract the most important ideas for you.
Yeah. Our goal today is to really help you understand what these intelligent agents are all about,
Exactly.
how they interact with the world around them, different ways to design them, different ways to think about them.
Right, and at the very heart of all of this is this concept of a rational agent.
Yeah.
And that right away begs the question, what does it even mean to be rational?
Right. So let's start with the basics. Agents and environments.
Okay,
Our source defines an agent pretty broadly as anything that can perceive its environment through sensors and act upon that environment through actuators.
okay, so it could be something as simple as us humans, right? Our eyes and ears are sensors,
Yeah.
our hands and feet are actuators.
Exactly. Or a robot.
Okay,
Cameras and rangefinders for sensors and then motors for movement.
and then even extending this idea, we can think about software agents.
Absolutely.
So something like maybe taking in data as sensory input.
Right, like the contents of a file or network packets.
Yeah.
And then its actions would be things like writing to files or sending out data packets.
Right, and then what about the environment?
So the environment is basically everything that's relevant to the agent.
Okay,
It's the part of the universe that the agent can perceive and interact with.
right, so technically it could be as big as the entire universe,
Yeah.
but for practical purposes.
Yeah, you have to kind of narrow it down a bit.
It's the stuff that the agent can actually sense and impact.
Right. And the way an agent interacts with this environment is through something called percepts.
Go ahead.
A percept is just the agent's sensory input at any given time.
Correct.
And then the entire history of everything the agent has ever perceived is called the percept sequence.
Okay, so the agent takes in this sequence of percepts, and then based on that, it chooses an action to take. And the way that an agent decides how to act based on those percepts is called the agent function.
Precisely. So the agent function is basically a mapping
Okay.
from any given percept sequence to an action.
So is that like the ideal, or is that...
Yeah, it's like the theoretical description of
Okay.
how an agent should behave in any given situation.
Okay, and that's different from the agent program.
Right, exactly. The
Yeah.
agent program is the actual implementation, the code that's running on the system.
Right, so that could be a smaller subset.
Yeah, exactly. It has to be practical.
Right.
So it's important to distinguish between the agent function, which is this abstract idea, and then the agent program, which is the concrete implementation.
To make this more concrete, the book gives a really helpful example, the vacuum cleaner world.
Ah, yes, a classic.
So we can just imagine a very simple setup with just two locations,
Yeah.
room A and room B, and each room can either be dirty or clean. And our little vacuum agent can sense which room it's in and whether or not there's dirt in that room.
And it has a few basic actions it can perform.
Okay,
It can move to the right, move to the left, it can suck up the dirt, or it can do nothing.
so an example of an agent function would be
Oh.
if the current square is dirty, then suck up the dirt, otherwise move to the other square.
Right, and you could actually list out the entire agent function.
Okay.
For example, if the agent senses that it's in room A and that room A is clean, then the action would be to move, right? If it senses room A is dirty, then the action would be to suck.
Okay.
And you would do this for every single possible percept sequence.
Right. And figure 2.3 in the book shows a little bit of what this might look like.
Right. And the cool thing is you could design all sorts of different vacuum world agents just by changing the agent function, just by changing that mapping between the percepts and the actions.
Now, the book makes a really interesting point about this idea of an agent.
Oh, yeah.
It says it's more useful to think of it as a way to analyze systems rather than some sort of strict categorization.
That's right. You could technically view a simple calculator as an agent.
Okay.
It takes input like 2 plus 2.
Right.
It processes that and it outputs 4.
Yeah. But that doesn't really give us much insight.
Yeah, it doesn't really help us understand the calculator in a meaningful way.
Right. So the authors are really interested in using this concept of an agent to describe systems that have significant computational resources and where the decision-making is non-trivial.
Right, where there's actual complexity involved.
So we have this idea of an agent perceiving its environment and acting upon its environment.
Right.
Now let's get to the heart of what makes an agent intelligent.
Okay.
This concept of rationality.
Yeah, a rational agent.
A rational agent. is one that does the right thing.
Okay, but then what does right mean?
Right. That's the question.
In AI, we typically define right in terms of consequentialism,
Okay.
which means we judge an agent's behavior based on the outcomes of its actions.
Okay.
So the agent takes an action that leads to a sequence of states in the environment.
Okay.
And if that sequence of states is desirable, then we say the agent has performed well.
Okay, so how do we determine what's desirable?
Well, that's where the performance measure comes in.
Okay.
The performance measure is what we use to evaluate how good a sequence of states is.
Okay, so it's interesting to think about the difference between humans and machines.
Right.
For us humans, our idea of what's rational is tied to our own desires and preferences.
Yeah.
But for machines, the performance measure is determined by the people who design them or the people who are using them.
That's right.
Now, the book mentions a really important warning from Norbert Wiener
Oh, yeah.
that we need to be very careful that the purpose put into the machine is the purpose which we really desire.
Absolutely. It turns out figuring out how to define that performance measure can be really tricky.
Okay.
Yeah. Let's go back to our vacuum cleaner example.
Okay.
So you might think that a good performance measure would be the amount of dirt cleaned up in, say, an 8-hour period.
Okay.
But a perfectly rational agent using that performance measure might just clean up some dirt and then drop it right back on the floor to clean it again.
Yeah, to maximize the amount of cleaning.
Exactly. Just to get a really high score on the performance measure.
Right.
And that's not really what we want.
Right. What we really want is a clean floor.
Exactly.
So a better performance measure might be to give the agent points for each clean square at each time step.
Right.
And then maybe subtract points for using too much energy or making too much noise.
Exactly. The key here is that you want to define the performance measure based on what you actually want to achieve,
Right.
not just on how you think the agent should behave.
Right. And even then, things can get a little bit complicated.
Oh, yeah, absolutely.
So the book gives the example that if we're measuring average cleanliness over time, an agent that does a mediocre job consistently might get the same score as an agent that cleans really intensely for a short period of time and then takes long breaks.
Right. So which one is actually better?
Right. Is it better to have maybe like extreme highs and lows or to have just kind of like this steady, mediocre performance?
Right. It starts to touch on some really deep philosophical questions
It really does.
about what we value.
Absolutely.
And for the most part in our discussion today, we're going to assume that we can define this performance measure correctly.
Okay.
But it's important to keep in mind that there's always this potential for these unintended consequences
Right.
if we don't get the purpose right.
Like the story of King Midas.
Exactly. And especially when you're dealing with software that's designed to be used by many different people, it's not always possible to know exactly what everyone's preferences are.
So what determines whether an agent is rational at any given moment?
So the book lists 4 key factors.
Okay.
The first is the performance measure itself. The second is the agent's prior knowledge about the environment.
Okay.
The third is the actions that the agent can perform. And the fourth is the agent's percept sequence up to that point.
Okay. And this leads to a formal definition of a rational agent.
So a rational agent should choose whichever action maximizes its expected performance given the evidence provided by the percept sequence and whatever built-in knowledge the agent has.
Okay, so let's go back to our simple vacuum agent that just cleans if it senses dirt and moves if it senses clean.
Right.
The book argues that under very specific conditions, that agent is rational.
What are those conditions?
So the performance measure has to be rewarding clean squares.
Okay.
It has to know the layout of the rooms.
Okay.
It only has the actions to move and suck, and it has to be able to accurately perceive dirt and its location.
Right. So in that very limited scenario,
Yeah.
it is rational.
But if we tweak those conditions just a little bit, then that same agent could quickly become irrational.
For example.
So if we introduce some sort of penalty for movement after all the dirt is gone, then the agent's behavior of continuously going back and forth would lead to a poor score.
Right. A more intelligent agent would recognize when the job is done.
Yeah, and stop moving.
Exactly.
Or if the layout of the rooms is unknown,
right.
the agent would have to explore and learn the layout.
Right, which our simple agent can't do.
Right.
That's a good point.
And this brings up a really important distinction.
Okay.
Rationality is not the same as omniscience.
Right.
So an omniscient agent would know the actual outcome of its actions.
With perfect certainty.
But that's just impossible in the real world.
It is.
The book gives this example of someone rationally deciding to cross the Champs-Élysées in Paris.
Okay.
Because they look around and there's no traffic.
Uh-huh.
But then, out of nowhere, they're hit by a falling piece of an airplane.
Oh, wow.
So was the original decision to cross the street irrational?
Probably not. You can't plan for everything.
Exactly. So rationality is about maximizing expected performance,
Yeah,
whereas perfection would be maximizing actual performance,
right.
which we just can't expect.
Yeah, you can't have perfect foresight.
Right. And so our definition of rationality really emphasizes that it depends only on the percept sequence up to that point.
Right.
So it means the agent is making the best decision it can based on the information it has at that moment.
Right. But that doesn't excuse a lack of intelligence.
Right.
So, for example, the book talks about not looking both ways before crossing a busy road.
Yeah.
Just because you don't see an oncoming truck doesn't mean it's rational to step out into the street.
Right. You should be gathering more information.
Exactly.
Like looking both ways before you cross the street.
Right, taking actions to improve your future percepts.
Exactly. And that's also why exploration is a rational strategy in an unknown environment.
Absolutely.
Like if our vacuum agent didn't know the layout of the room.
Right, it would have to go and explore.
Now, a truly rational agent also needs to be able to learn from its experiences.
Yes, learning is crucial.
So its initial programming might include some basic knowledge, but as it interacts with the environment, it should be able to update and refine that knowledge.
Right, that's what sets it apart from agents that are just purely pre-programmed.
Right. The book gives some really interesting examples from biology.
Oh, yeah.
So like the dung beetle
Okay.
that tries to plug its nest with a ball of dung, even if the ball is removed while it's in the middle of the process.
Oh, wow. So it just keeps going through the motions.
Yeah, it can't adapt.
Yeah, no learning there.
Or the sex wasp
Okay.
that has this very specific routine for burying a stung caterpillar.
Ah.
But if you move the caterpillar while the wasp is checking its burrow, it'll just repeat the steps over and over again.
Wow, it never learns that the plan is failing.
And these examples really highlight the limitations of agents that just rely on this pre-programmed knowledge.
Right, they can't adapt.
And that leads to the concept of autonomy.
Yeah. So an agent is autonomous to the extent that it relies on its own percepts and learning,
Okay.
rather than just knowledge that was put in there by the designer.
So a rational agent should strive for autonomy
It should.
to compensate for whatever initial knowledge it was given, which might be incomplete or even incorrect.
Right, like a vacuum cleaner that learns where and when new dirt tends to appear
Yeah.
will do a much better job than one that's just following a fixed schedule.
Right. But obviously we can't expect complete autonomy right from the start.
Well, yeah, an agent that has absolutely no experience at all would have to just act randomly at first.
Right.
Just to gain some information.
And so just like animals are born with certain reflexes, to help them survive long enough to learn, it often makes sense to give AI agents some initial knowledge to bootstrap the learning process.
Right.
So the real power of learning is that it allows us to design agents that can succeed in many different environments. Okay, so now that we have this good understanding of what makes an agent rational, let's shift our focus to the environment itself,
Okay.
and more specifically, the task environment.
So the task environment is basically the problem that the rational agent is trying to solve.
Okay.
And it includes everything that is relevant to the agent achieving its goals.
The book introduces a really helpful framework
Okay.
called PEAS,
Yes.
which stands for Performance, Environment, Actuators, and Sensors.
So whenever you're thinking about designing an agent, you should always start by defining these 4 things.
Okay, so let's take a more complex example than our vacuum cleaner,
Okay.
an automated taxi driver.
Okay, great example.
So the performance measure here would be things like safety, getting the passenger to their destination, quickly obeying traffic laws, maximizing profits for the taxi company, and minimizing negative impacts on other road users.
Right. And there's often trade-offs between those things. You can't always have everything.
Exactly, and the environment would be everything the taxi operates within.
Right. So the roads themselves, other vehicles, pedestrians, traffic lights, police officers, the weather conditions.
Yes, so many things.
The passengers themselves.
Yeah.
And this can all change dramatically based on the location and the time of day.
Right, and then what about the actuators?
So the actuators are how the taxi interacts with its environment.
Okay.
So the steering wheel, the gas pedal, and the brake, the turn, signals the horn, maybe a display to communicate with the passengers, and maybe even a voice communication system.
And then finally, the sensors.
So the sensors are how the taxi perceives its environment.
Okay.
Cameras, radar, LiDAR, speedometer, GPS engine sensors, microphones, and maybe even a touchscreen interface for passengers to use.
Okay, and figure 2.4 in the book shows examples of this for different types of agents.
Right. It gives you a good overview.
Now, task environments can be categorized along several key dimensions.
Yes, they
And
can.
these categories are really important because they can heavily influence the design of our agent.
Mm.
So one dimension is whether the environment is fully observable or partially observable.
So if an agent can perceive the complete state of the environment at all times, then it's fully observable.
Okay.
But if some information is hidden or the sensory data is noisy or incomplete, then it's partially observable.
So our vacuum agent that can only sense dirt in its current location would be an example of a partially observable environment.
Right. And so is a taxi driver who can't perfectly predict what other drivers are going to do.
Right.
Or think about a self-driving car,
Yeah.
trying to figure out what's around a blind corner.
It doesn't have all the information.
Exactly.
Another important distinction is between single-agent and multi-agent environments.
So solving a crossword puzzle is generally a single agent problem,
Okay.
but playing chess involves two agents.
Right.
And it can get tricky when you have to consider whether other entities in the environment are agents themselves with
Right.
their own goals.
Right.
Or are they just objects that behave according to the laws of physics?
Right. So chess is clearly a competitive multi-agent environment.
Yes.
But something like taxi driving is a little more complicated.
Right.
Because it's partially cooperative.
Yeah. Avoiding accidents benefits everyone.
Right. But it can also be competitive.
Yeah, if multiple taxis are trying to pick up the same passenger.
Right.
Exactly.
Okay, then we have deterministic versus non-deterministic environments.
So if the next state of the environment is completely determined by the current state and the actions the agent takes, then it's deterministic.
Okay.
But if there's some randomness involved, then it's non-deterministic.
Okay.
Our vacuum world, as we've described it so far, is deterministic.
Okay.
But a real-world scenario like taxi driving with traffic and unexpected mechanical problems is definitely non-deterministic.
Right. And the book also distinguishes between non-deterministic and stochastic environments,
Right.
where the probabilities of different outcomes are known.
Exactly.
Then we have episodic versus sequential.
Right.
So in an episodic environment, the agent's experience is broken down into these atomic episodes.
Oh.
Okay.
And the outcome of one episode doesn't affect the next?
Okay, like inspecting parts on an assembly line.
Exactly.
Whereas in a sequential environment, the agent's current actions can have long-term consequences.
Yeah, like in chess or taxi driving,
Right.
your previous moves matter.
Right.
Sequential environments tend to be more challenging.
Because you have to think about the future.
You do.
Okay, environments can also be static or dynamic.
So in a static environment, the environment doesn't change while the agent is thinking?
Okay, like a crossword puzzle.
Exactly.
But in a dynamic environment, things are changing while the agent is deciding what to do.
Yeah, like in taxi driving,
Right.
where traffic conditions can change really quickly.
Right, and the book mentions semi-dynamic environments,
Right.
where the environment itself doesn't change, but the agent's performance score might.
Exactly. Like in chess with the timer.
Right.
The board doesn't change, but your time is running out.
And then we have discrete versus continuous.
So this refers to whether the state of the environment time, the agent's percepts, and the actions are all discrete or continuous.
Okay, so chess is a good example of a discrete environment.
Yes.
Finite number of states and moves.
Right.
But taxi driving, with its continuous range of speeds and locations, is continuous.
Exact.
And finally, we have known versus unknown.
So this refers to the agent's knowledge about the laws of physics of the environment.
Okay, so this is different from observability.
It is.
You could have an environment that's fully observable but unknown.
Like when you start playing a new video game.
Right, you can see everything on the screen.
But you don't know what the controls do, whereas solitaire is known.
Okay.
You know the rules,
Right.
but partially observable.
Because you can't see all the cards.
Exactly.
And the book even mentions the possibility of an unknown performance measure.
Right, which adds a whole other layer of complexity.
It really does.
The book points out that the most challenging environments are those that are partially observable, multi-agent, non-deterministic, sequential, dynamic, continuous, and unknown.
In taxi driving is pretty close to all of those.
Is.
And figure 2.6 in the book has a table that summarizes these properties for different environments.
Right, a really helpful table.
So now that we've explored the different types of environments an agent might face,
Yeah.
let's talk about the structure of agents.
Okay, so how are these agents actually built?
Right, so we've talked about how agents behave.
Yeah,
Now we need to talk about how that behavior is generated.
right.
So the agent program is the set of instructions that implements the agent function.
Uh-huh.
And that program runs on what's called the agent architecture.
Okay.
which includes both the hardware and software.
Right, the physical stuff and the code.
Right. So an agent is its architecture plus its program.
Makes sense.
And so typically the agent program takes the current percept as input and returns an action as output.
Right. But it's important to remember that while the program only sees the current percept, the agent function might depend on the entire percept history.
Right. So if the agent needs to keep track of its history, the program has to have a way to remember that.
Yeah, it needs some sort of memory.
Now, the book introduces this idea of a table-driven agent program.
Okay.
And this is more of a conceptual model.
Right.
So the idea is that the agent would keep track of every single percept sequence it's ever experienced,
Okay.
and then use that sequence as an index to look up the correct action in this massive table.
So this table would basically be the agent function. It
Right.
would have all the
So
answers.
this is obviously not feasible
No, not
or
a...
anything other than very simple toy problems.
Right. Imagine trying to store every possible percept sequence for something like driving a car.
Right.
The table would be astronomically large.
Way too big.
You could never build it.
And even if you could never store it.
No way.
So while this table-driven agent is impractical, it's a useful concept.
It is.
Because it shows that, in theory, at least, you can create an agent function that would produce perfectly rational behavior.
Right. The challenge is to come up with something more efficient.
Right.
Something that can approximate this ideal behavior without needing this massive lookup table.
And the authors think that we can do that.
They do.
And they present 4 basic kinds of agent programs.
Okay.
Simple reflex agents, model-based reflex agents, goal-based agents, and utility-based agents.
Let's start with simple reflex agents.
Okay.
These agents select actions based on the current percept only,
But-
completely ignoring the percept history.
So our simple vacuum cleaner agent.
Exactly.
That sucks if it senses dirt and moves otherwise would be an example of it.
Right. And figure 2.8 in the book shows a diagram of what this type of agent might look like.
Okay.
Very simple.
So these agents work by using condition action rules.
Right. If-then statements.
Exactly.
So like if car in front is braking, then brake.
And even humans use a lot of these reflex-like responses.
We do. Some of them are learned like driving.
Yeah.
Right.
And some are innate, like blinking when something gets too close to your eye.
Right. And these rules can be implemented in many different ways.
Yeah, from simple if-then-else statements to Boolean circuits to neural networks.
So these simple reflex agents are very computationally cheap and easy to implement,
They are.
but they have limited intelligence.
Yeah, they only really work well in fully observable environments.
Right.
If the agent can't see everything it needs to, it can run into problems.
Right. So for example, our braking rule assumes we can reliably tell if the car in front is braking.
Yeah, but in reality, it might be hard to tell.
Right, because of different car models, lighting conditions,
Right.
and our location-blind vacuum agent that we talked about before could
Yeah.
easily get stuck in an infinite loop.
Right, just going back and forth between the two squares.
Right.
Now, the book mentions that adding some randomness to the agent's actions can sometimes help it escape these loops.
Okay.
So, for example, our vacuum agent could randomly choose left or right when it doesn't sense any dirt.
But while this might work in some cases, it's not really the most rational approach compared to more sophisticated methods.
Okay, so to handle partially observable environments, we have model-based reflex agents.
Right. So these agents keep track of an internal state,
Okay.
which is basically a representation of the parts of the world that it can't see directly.
Okay, so going back to our braking example, a model-based agent might store the last few frames from the camera.
Exactly.
So it could compare the current frame to the previous frames to better detect brake lights.
Right. And that would make its braking response more accurate.
So to do this, the agent needs 2 things.
Okay.
A transition model, which describes how the world changes over time,
Okay.
and a sensor model, which describes how the state of the world is reflected in the agent's percepts.
Right. And figure 2.12 in the book shows a diagram of this type of agent.
Okay, so using these models, the agent can try to maintain an accurate representation of the world.
Exactly.
But it's important to note that this internal state is often the agent's best guess about the real world,
It is.
not a perfect representation.
Because it's partially observable.
Right. It doesn't have all the information.
Exactly.
Now, even knowing the current state of the world isn't always enough to decide what to do.
Right. Sometimes you need goals.
Okay, so this is where goal-based agents come in.
So these agents have some sort of goal information in addition to their representation of the current state.
Okay.
So this goal information describes situations that are desirable,
Good.
like reaching a particular destination.
And figure 2.13 in the book shows a schematic for this type of agent.
Right.
So goal-based agents use their model of the world to choose actions that will eventually lead them to achieving their goals.
Exactly. And this often involves some sort of planning.
Right, especially if the goal is not immediately achievable.
Right. You need a sequence of actions.
And what really sets goal-based agents apart from reflex agents is that they're thinking about the future consequences of their actions.
Exactly.
So they're thinking, what will happen if I do this?
Yeah.
Will this get me closer to my goal?
Right. Whereas reflex agents are just reacting to the immediate situation.
Right.
No real thought about why they're doing what they're doing.
Exactly.
Now, you might think that goal-based agents are slower or less efficient than reflex agents in simple situations,
Okay.
but they're much more flexible.
Right.
So if you want your taxi driver agent to go to a different destination, you just change the goal.
Okay.
But with a reflex agent, you would have to rewrite all of its rules.
Okay, so goals are clearly important,
They are.
but even goals have limitations
They do.
because simply achieving a goal doesn't tell us anything about the quality of the behavior.
Right. So just getting to a destination doesn't tell you if the journey was fast or safe or cheap.
And this is where utility-based agents come in.
Right. So utility-based agents use a more general performance measure that evaluates how happy the agent is in different states.
Okay.
And the agent's utility function is basically its internal representation of that performance measure.
Okay, so if the agent acts in a way that maximizes its utility,
Yeah.
it will be rational, according to our earlier definition.
Precisely.
And figure 2.14 in the book shows a schematic for this type of agent.
It does.
Now, utility-based agents are really useful in situations where there are multiple, potentially conflicting goals,
Right.
or where the outcomes of actions are uncertain.
Like in our taxi driver example.
Yeah.
The agent might want to get to the destination quickly, but also safely.
Right, and those two goals can be in conflict.
They can.
So a utility function provides a way to balance those.
Exactly.
And they can also take into account the likelihood of different outcomes.
Right.
When no single action can guarantee success.
Exactly.
So the agent should choose the action that maximizes its expected utility.
Right. You have to average over the possible outcomes.
And the book even says that any rational agent must behave as if it has some underlying utility function that it's trying to maximize.
That's a really interesting point.
It is.
Now, while the concept of maximizing expected utility sounds simple,
Yeah.
actually building these agents is really complex. They need sophisticated ways to represent the environment,
Uh-huh.
to reason about the world, to learn from experience.
And the book also mentions that not all utility-based agents are model-based.
Right.
There are model-free agents that can learn what to do without explicitly building a model of the world.
That's right.
Okay? And now we come to learning agents.
Yeah, so the idea here is that instead of trying to program intelligent machines by hand,
Okay.
we should build machines that can learn from experience.
Right.
This was actually an idea that Alan Turing had very early on.
Oh, wow.
And now, in modern AI, machine learning has become the dominant approach for building advanced systems.
Now, the key advantage of learning is that it allows agents to operate in environments that they know.